Hi, welcome back to Physics Teacher. This is a question on the Sir Isaac Newton contest, which is a high school physics contest from Waterloo University. And in this question, 80% of the students attempted the question, and of those 80%, about half got it right. Give it a try, and I'll be right back with the solution. Alright, so this question is worded as sort of an extremely long slope that goes from Victoria to St. John's. So a 5,000 kilometer slope. So something like this, where this length here is 5,000 kilometers. And the height difference is only 3 meters. So there are a couple ways you can answer this question. First of all, you can do conservation of energy. Now in this case, there's no friction, so it says ignore friction, ignore the curvature of the Earth, ignore air resistance, all that. So it's just an acceleration problem. And so if you wanted to, we know that at first it's at rest, so its initial velocity is at rest, and we can figure out what its final velocity would be using conservation of energy. So the total energy here at point A would be equal to the total energy here at point B. So at A, we have all gravitational potential, mgh, and at B, it's all converted to kinetic energy, 1/2 mv squared. Masses will cancel, and we can rearrange to solve for V as the square root of 2gh, and since h is 3, that would just be the square root of 6g. And then you can solve for time using one of your equations for uniform acceleration, where displacement is the average velocity, initial plus final, divided by 2 times time. So if we do that, initial will be 0. And we can rearrange this. So multiply both sides by 2. We have 2 delta t equals final velocity times time, or divide both sides by final velocity, and we get time equals to 2 times delta d, which is 5,000 kilometers, all divided by that final velocity, which is the square root of 6 times 9.81 meters per second squared. And we would have to change this kilometers into meters, so let's multiply that by 1,000. And that gives us about 1.3 times 10 to the 6 seconds. Now there is another way you could have done this. If you didn't like energy conservation, you could have done forces. So in this case, if we were to look at this free body diagram, we would have had gravity down, mg, and the normal force up on your angle. And we could choose a coordinate system that is slanted with the incline. So that'll be our positive x direction. And this is our positive y direction. And we split gravity into its components with our coordinate system, where this is going to be the same angle as the incline itself. And then you can use Newton's second law, where the sum of all forces in x equals mass times acceleration in x. And your force here is just this component of gravity, which is mg times the sine of theta, and that equals ma. So masses cancel, and you can solve for acceleration. Now you do need to know theta first, so what you would do is you would solve for this theta, using sine of theta is opposite over hypotenuse. So it's 3 over 5,000. Just again, convert kilometers into meters. So you would have g times, so opposite 3 over 5,000 times 1,000. And that'll equal acceleration. And then once you have acceleration, you can use a different equation for uniform acceleration to get time, but you'll end up with the exact same value of time. And once you have time, obviously we don't have seconds here, so we just need to convert this. And when you convert it, you get about 15.04 days, or rounded to C, 15 days.